The heart has electrical activity because we know that its contraction and relaxation, it being excitable, its contraction and relaxation depends on electrical impulses. So what is known is that when these impulses are being produced, they can actually spread through the nearby tissues, meaning the impulses from the lungs, they can cause depolarization of the tissues around them, and they can spread throughout the body, meaning if you use electrodes, you can detect electric currents on the surface of our skins. And this was discovered by a man called Einthoven. And if you look at this illustration is showing his machine. So to prove that electric current, that the body is at some point of time the body is charged or it is polarized and depolarized, he used this machine to measure electric potentials between 2 points of the body. So he got the hand, he put it in a solution, a conducting solution, one electrolyte, the left arm, the right hand, and the left leg. So he used this machine, which was an amplified voltmeter, to measure the potential differences, for example, potential differences between the left hand and right hand. So he realized that with time, the electric potentials went on varying. And varying electric potentials meaning the electric current goes on reducing and increasing. And this was his finding, the first electrocardiogram that was recorded by this machine. So from his experiment, he proved that actually electric currents that are produced by the heart, they spread through nearby tissues and they reach the surface of the skin. That's how he was able to determine these different electric potentials. So right now we have modern electrocardiography where they are using a modified machine, a modernized machine that is able to detect these changes in electric potential in millivolts in an amplified way and in a better way. If you look at this illustration, these are leads of the electrocardiogram. And what you're going to be basically looking at in this video is electrocardiography actually. So you see that some leads are placed on the chest, some are placed on the arm. So the importance of these leads actually, we are measuring the difference in voltages between 2 points on the body. It's important to note that electric potentials or potential differences, we are measuring differences in voltages between 2 points of the body. So if you look at this ECG showing difference, when it is moving up and down, it is showing how the voltages are changing, the difference in voltages. So you're going in electrocardiography actually you realize that we can use the electrical activity of the heart to find out what is happening inside the heart. So to understand this basic concept of interpretation of the ECG, it is important you know of the excitatory and conduction system of the heart. So it is widely known that we have the pacemakers, and the main pacemaker is the synatrial node. And it is known that the heart it contracts and relaxes independent of the control of the brain, what we call autorhythmicity, meaning the contractions of the heart, they are actually initiated by the heart itself, and that's how heart transplants are done. And that even independent of control of neurons, if the heart is taken out of the body, it can still contract and relax. And those impulses are mainly initiated by the synatrial node. Though in pathological cases, if the synatrial node is damaged, you know that the AVN and band of His is the same as the AV band. And the Purkinje fibers, they also have ability of initiating signals, though at a very low heart rate. So actually the excitatory parts of this system are the synatrial node, the AVN and the band of His. Then this basically it is just a conductive system. These fibers, we have the internodal pathways. They are called internodal because they are between two nodes, the synatrial node and the atrial ventricular node. From the AVN, we have the band of His. Then the band of His will divide into two main bundle branches, bundles of fibers, the right bundle branch and the left bundle branch. Left bundle branch will supply the left ventricle, right bundle branch will supply the right ventricle. So that's the brief functional anatomy there. So actually what happens for the sinus node, you know that the impulse that causes the heart to respond through contraction and relaxation starts from the synatrial node. I think that then it will spread through the internodal pathways to the AVN. From the AVN it goes to the band of His. From the band of His, then it splits into to giving you the right bundle branch and the left bundle branch, which still divides further into the Purkinje fibers that then will spread the impulses to the ventricles. You realize that with the importance of this conduction system, that however much these impulses can still flow, the depolarization may still flow through individual cells of the heart. They cannot flow from the cells of the atria to the cells of the ventricle. This can be illustrated in this illustration. If you look at this is our synatrial node. This is the synatrial node. Impulses are going to spread from the synatrial node towards the cells. So we look at these as the contractile cells. So these are the cells of the atria. So when depolarization when this impulse is generated, you know that excitable cells respond by through depolarization, meaning the sodium metal channels open, sodium ions rashly enter inside. And you know that at the resting phase, the cells are polarized, meaning that inside is negative and outside is positive. So actually a polarized cell, we look at it that its membrane outside is positive but inside is negative. But upon the impulse reaching the cardiac cells, they will depolarize. And you know that these cells are connected by gap junctions, meaning the sodium ions that have entered through this cell, they can actually spread. They can spread and go to the next cell, to the next cell. So the wave of depolarization will flow through the cells of the atria as they are connected. But as they reach the atrioventricular junction from the atria to the ventricles, they cannot spread through. There is a blockage, meaning they can only pass through. The impulse from the sinus node will only reach the ventricles through this conduction system. This is important to explain the blocks as we shall discuss them later. So these impulses that are generated by the synatrial node, they have to be conducted. So if you look at the heart muscle, has two types of cells. We have cells that are able to generate the pulses, or you can say that cells that are excited, that can produce the impulses, but we also have contractile cells that don't produce impulses, they simply contract. So if you look at the sun, the AVN, the band of His, the Purkinje fibers, the bundle branches, they themselves, they cannot contract. Hope you know what that means. Meaning when they are excited, they respond by simply transmitting the impulse, but they don't contract. Then and these are the cells that are making up our conduction system, excitatory and conduction system. Then the rest of the cells which are not part of this system, they are contractile. They respond by contracting. Hope that is clear. So someone may still have a question that how is the synatrial node able to fire impulses continuously, rhythmically? That is from cardiophysiology. And the explanation say that it is mainly due to the Fanny currents. The Fanny currents that we talk about in the pacemakers. The first thing you note that the pacemaker cells, they don't have a constant resting membrane potential. For other cells, you expect that this phase 4 is going to be constant, but for the pacemakers, it is always changing. And why these sodium channels? It is the sodium channels, the slow-gated sodium channels that are responsible for this phase. And they are actually the ones that are responsible still for the rhythmicity of the heart. So these channels of we call them hyperpolarization activated sodium channels. What that means that for them, whenever the cells of the pacemakers are hyperpolarized, they start opening. That is when they open. So they are activated by hyperpolarization. So when they start opening, since they are slow, the membrane potential goes on increasing slightly. Now, when it reaches the threshold, that is when the first calcium channels open, causing firing an impulse. So here at phase 0, this is when the impulse has been fired from the synaptic node. They knew that this depolarization after entry of calcium ions, since for them they don't contract, the entry of calcium ions does not cause a plateau phase. Like it is short-lived. Then after we look at phase 3 where potassium ions will start coming out, causing the cell to polarize again. But as it is polarizing, it goes below the threshold to a more negative value, what you call hyperpolarization. And immediately the cell is hyperpolarized, the finite current sodium channels, they start opening and the cycle repeats. What do you need to pick from this in this topic? Whenever the impulse is fired, that is when the cycle is going to begin. I mean the atrial contraction followed ventricular contraction, they start at firing of the impulse from the synaptic node. And you know that during any cardiac cycle, the impulse is fired once normally. Meaning by the time another impulse is going to be fired, we expect that this is a complete cardiac cycle, a complete heartbeat from phase 0 to phase 0. You notice that, meaning it will take an average of 0.8 seconds, which are equal to one heartbeat. So the pacemakers, they lack phase 1 and phase 2. That is how the synaptic node is always able to fire impulses continually. Whenever the impulse is fired, you should know that an impulse is followed by depolarization, and depolarization is followed by contraction, and the opposite is true. When repolarization takes place, that is when relaxation will take place in the cardiac cells. But if you look at other cells, they have a different action potential, different from that of the pacemaker cells, and it looks like this. Than for the normal cardiac cells. For them, they have a steady resting membrane potential, which is this negative 96. So the action potentials in the rest of the fibers of the heart will only be fired if the impulse from the synaptic node has reached. So if the impulse reaches, that is when the action potential of these ventricular muscle fibers will be fired. So you see that this phase 0 sodium ions enter rapidly. Then as after this rising phase, as potassium ions are moving out like in the normal action potential of the nerves, you know that what causes the plateau phase, the potassium ions move out while the calcium ions are entering. And you know that the importance of calcium ions is the important in muscle contraction, meaning throughout this plateau phase, this is when muscle contraction is taking place. Then a time will come when calcium ions will start being exported out of the cardiac cells by those sodium calcium exchangers. Calcium ions are also taken back into the endoplasmic reticulum, but potassium ions will continue moving out, causing repolarization. So this is the normal action potential of the cardiac muscle fibers. This is also important, especially in understanding the ECG, that When you look at this conduction system, we are going to concentrate at the part of the AV node. The impulse is coming from the synaptian node. Then these fractions you are seeing, we are expressing a fraction of 1 second. You know that, hope you know it in your head, that the whole cardiac cycle will take place in less than 1 second. So all these phases will take place in decimals of a second, of 1 second, which are fractions. So from the synaptian node, the impulse has come to the internodal pathways. So by around 0.03 seconds, it has already reached the atrioventricular node. Meaning from the 0.8 seconds that would take the whole cardiac cycle, only 0.03 is already at the AV node. I want you to notice something. By the time the impulse reaches the bundle branches, what was 0.3 is 0.16, meaning the impulse has been delayed through this system. The impulse will be delayed in the AV node, and one of the reasons is that the cells in the AV node, first thing, they have few gap junctions, meaning the depolarization takes a longer time. Since the gap junctions are few, the depolarization will be slowed. Number two, the cells in the AV node and in the band of His, or the AV band, they are tightly packed, and that increases electrical resistance. So also the impulse will be delayed. And number three, the cells in this system have a very negative resting membrane potential. So that is what causes the delays through this system. And this will relate to how they come up with the normal value of the PRI interval when you reach to the ECG. So in the AV node itself, it will be delayed for 0.09 seconds, the impulse. Then in the AV band, it will be delayed for a further 0.04 seconds, meaning by the time you reach the band branches, you have taken a total delay of around 0.13 seconds. So the impulse which reached at 0.03 will reach the ventricles at 0.16. And if you also add on the initial delay from the synaptian node to the AV node, which is around 0.03, the total delay from the impulse being fired to each reaching the ventricles will be a total of 0.16 seconds. That means that from the firing of the impulse to the depolarization of the ventricles, we expect at least 0.16 seconds. What does that imply? That if this time is greatly increased, that is a sign of increased resistance through the system, or even blocks, meaning the impulse is moving with greater resistance. So this is just a bigger picture. From the synaptian node to the AVN, it is 0.03 seconds. You're also seeing that time. So the impulse has to first spread through both atria, then it is collected through both atria. So the impulse spreading in the atria cells themselves, it is not actually passing through this conduction system. Then the conduction system will conduct it to the AVN, where it will be delayed by over 0.1 seconds. So by the time it reaches the bundle branches, it's around 0.17. So we know the importance of this delay is that it allows the both atria, to contract before the ventricles have contracted. How is it related? We said earlier that the ventricles or muscles will only contract when the impulse has reached. So you find that by the time the impulse is being delayed in the AVN, both atria have already received the depolarization wave and they have already contracted. So during the time when, the flow through the Purkinje fibers themselves and bundle branches is very rapid. So actually, by the time the impulse will reach the ventricles will be contracting while the arteries are relaxing, meaning it will take place at the same time. But the contraction of the atria takes place before the ventricles have contracted due to this AV node delay. So this is that was just an introduction or a simple review that can help you easily understand how to interpret the electrocardiogram. Said that the impulse flows through the conduction system. Hope you notice that delay that is taking place at the AVN. This causes the, as you see, that atria will contract, followed by the contraction of the ventricles, and that is that the advantage is mainly expounded during discussions on the cardiac cycle. So back to our electrocardiogram. I want you to notice that we say that on the electrocardiogram we are recording potential difference between 2 points on the body, because this impulse from the heart will spread throughout the tissues of the body and body fluids. So when you're measuring potential difference between 2 points, there is a time when the potential difference increases and a time when it decreases. So we are going to relate these changes in potential differences to the activities that are taking place inside the heart. You need to know, how does the ECG work? How do we get upward waves, downward waves? Why are some waves taller than the other? Why some waves shorter than the others? And also to interpret, helps you to interpret pathological conditions, to know that if the wave behaves in this way, it implies this. So you're going to use a simple voltimeter. A voltimeter has a negative terminal and a positive terminal. You note that. When will the voltimeter give you a positive deflection? A voltimeter only gives a positive deflection if its positive terminal is in a more, should I say, in a place which has a higher voltage, and if the negative terminal is at a point which has a lower voltage. In simple terms, the voltimeter will only give you a positive deflection, and on our ECG, positive is moving upwards. You know, this is the y-axis is representing voltage, meaning if the wave is going up, meaning the voltimeter is showing an increase. If the wave is going down, it means the potential difference is reducing. That is the simple science behind it. So whenever, if you are having two terminals, because we are going to go to the leads, limb leads, precordial leads, if you have two terminals, if the positive terminal is at a point which is more positive, and the negative terminal at a point which is more negative, that is when it gives you an increase, an upward going wave. So from, we say that during at resting membrane potential, when the cells have not yet been excited, the inside is negative, the outside is positive. So this side is depolarized, this side is polarized. So the wave is flowing from that. This is the depolarization wave. Why? It is causing the cell to become depolarized. It is flowing in this direction. So how we usually interpret it in simple terms, whenever the wave of depolarization is going towards the positive terminal, it will give you a depolarization wave which is upgoing. Meaning the opposite is true. If the depolarization wave is moving towards the negative, away from the positive, then it will be downgoing. Meaning having an ECG with an upward wave and downward wave, it does not simply define whether it is depolarizing or repolarizing. A repolarization wave, another T wave, is upward going. And we also have the depolarization wave of P wave, which is also upward going. So when you're using a certain limb lead, for example, if you use lead 2, we shall discuss it later, but to hint on it, whenever a wave is going upward, it means two things. It means that the wave of depolarization or the electric current is flowing from the negative terminal of that lead towards its positive terminal. If the lead is moving in an opposite direction, it will give you a downward wave. That is how we are able to interpret pathological cases. For example, if you know that during atrial depolarization, it has to be upward. If it is going downward, it simply means that the electric current is moving in the opposite direction. That is that. Number two, these waves they all have peaks. The peak will take place at a point when the distance, for example, now we are looking at this is negative, this is positive. If half of this area between these two terminals is half depolarized or half polarized, that is when it gives you the maximum potential difference. And that is from physics. Meaning, as it is going towards the positive terminal, it goes on increasing. When it reaches the middle, it is at its maximum. When it continues towards the positive terminal, it starts decreasing. Though we are not going to go into the details. Why is it that the depolarization wave reaches its peak when it is half depolarized? The explanation mainly is in electricity when you're measuring potential differences. Meaning at this point here, the depolarization, half of this rod has been depolarized. Hope that has been noted. When will the voltmeter give you a 0 millivolt? It will give you 0 millivolt if the negative terminal and positive terminal, they are both in the same regions of charges, equal charges. If the negative is, this side is negative and also this side is negative, that is when it goes back to the zero baseline. So this baseline you're saying is the 0 millivolt line. When does it come to the zero? Meaning simply means that if you have a constant wave on our ECG, which is flowing along with this zero baseline, it simply means that either the whole of the heart is having the same charge, or the area you are looking at is having the same charge. It is either fully depolarized or fully polarized. Those two cases, because when the whole heart is fully depolarized, the negative and positive terminals of any lead will be along the baseline, meaning the potential difference will be zero. That is for the depolarization. When you go for the repolarization, this is a repolarization wave. Why? Say that repolarization meaning we are making the membrane to become polar again, repolarizing. At first it had been depolarized. So if you look at this side, inside is negative, outside is positive. This part is polarized and the wave is making, actually this wave is making the inside negative. That is why we are calling it repolarizing. If you look at this first wave, it was making the inside positive, meaning it was a depolarizing wave. So whenever a repolarizing wave is flowing towards the positive terminal, the wave will be downward going. So these details are important, though they look trivial. Whenever a repolarizing wave, meaning that if you look at the heart, if the heart is being repolarized again, and the wave is moving towards the positive terminal of that lead, it will show you a downward wave. Here, depolarizing, if it is depolarizing going towards the positive, it will be upward. But if it is repolarizing, it will be the opposite. So the opposite is true. If the repolarizing wave is going towards the negative, it will also give you upward, like this depolarizing. So how can we summarize it? How can we easily understand it? A depolarizing wave favors the positive terminal. A repolarizing wave favors the negative terminal. Why am I using favoring? If the repolarizing wave is going towards the negative terminal, it will give you a positive deflection. If a repolarizing wave is moving towards the positive, repolarizing is favored by negative, but if it is going towards the positive terminal, that is when it gives you a downward deflection. The same thing for this last illustration. If the negative and positive, they are in areas of the same charge, it will go back to the zero baseline. If you understand this basic principle, ECG becomes easier. So here, in summary, started with a depolarization wave. When half the rod is depolarized, it will be at its maximum. Then it goes back to 0 because now the charges are equal. Then the repolarizing wave has started here. Since it is going towards the positive, remember this is positive, this is negative. Since it's going towards the positive, it is downward going. When half of the rod is polarized, the wave is at its maximum point. As it tends towards still the terminal, then it goes back to 0 baseline when both areas have equal charges. So if this is our heart, if we use this as an illustration of the heart, the inside has been depolarized. The central part of the heart has been depolarized. Why? Because it is negatively charged on the surface. Being negatively charged on the surface simply implies that inside has been made positive. I don't know whether you get that. So this region, whenever you're seeing a negative minus signs put on the heart, meaning that region has been depolarized. Then the rest of the regions which are still polarized, for them inside will be negative, but outside is positive. So now let's imagine if these are our voltmeters. If the negative terminal, look at this, if the negative terminal is in the positive, but the positive terminal is in the negative, that will give you a negative potential difference. What does it mean? To get a positive potential difference, the positive should be in the positive and the negative should be in the negative. Like for this voltmeter. But if the negative terminal and positive terminal are both in areas of the same charge, the potential difference is 0. So that's what we are recording, we are summarizing in the other illustration. Areas of the same charge, 0 potential difference. Meaning on our ECG, it will be along the baseline. If the positive terminal is in a more negative side, but the negative terminal is in the more positive side, it is negative. The potential difference will be negative, meaning the millivolts, actually on our ECG, the wave will be going down. That means it is going to the negatives, meaning the wave, our positive terminal in that case will be in an area of negativity compared to the negative terminal. Hope you get that illustration. Still, to bring it closer, we're looking at this as our heart. Inside, you look at this septum has been depolarized, and you see how they show that it's depolarized. They have put negatives outside. Then the rest of the heart is still in polarized state. That is why it is positive. So always when the electric current, the electric current flows from the heart, the electric current has a specific direction it flows. It will always flow from the depolarized region to the polarized region. So for most of the time, since the impulse comes from the synatrial node at the base of the heart, meaning always the impulse will be flowing from the depolarized region, meaning from the atria towards the ventricle. So meaning our electric current is flowing from the base towards the apex. You notice that? Areas of electronegativity, that is where depolarization has taken place, making outside negative. Areas of electropositivity, they are still polarized, meaning the impulse has not yet reached there. So from this illustration, we're having our negative terminal this side, positive terminal this side. Since the depolarization wave is flowing from the base to the apex, we are seeing that our positive terminal is in a region of positivity, but the negative terminal is in a region of negativity. That will give you a positive deflection on our voltmeter. So now instead of our voltmeter, we're going to be using the electrocardiogram. But these illustrations are for you to understand the ECG. So now this is the ECG, the standard electrocardiogram as mainly recorded by the lead 2, though even lead 1 and lead 3 it is almost the same. The P waves and T waves, they are almost the same. The difference is about the QRS. But for the standard limb leads, lead 1, lead 2 and lead 3, the ECG is almost the same. The difference is in amplitude, but the shape is the same. So from summary, you know that the P wave is representing atrial depolarization. QRS wave, this complex, QRS complex represents atrial depolarization. T wave representing repolarization of the ventricles. So actually what you want to internalize to see that how did they realize that the P wave is for atrial depolarization, QR is for ventricular depolarization, and T wave is a repolarization wave. We start from the principle we said that if the depolarization wave is going towards the positive terminal of the lead, it will be upward going. Remember that QRS QRS is also a depolarization wave. T wave is a repolarization wave because you know that the relaxation of the atria takes place during the contraction of the ventricles. So we don't see a visible wave for the repolarization of the ventricles since it is masked by the QRS complex. How did they find out which one represents it? Simply how to know how to interpret that this is the time for contraction, this is the time for relaxation. They plotted the action potential of the ventricle at the same time with the ECG of the ventricle. So it was noted that at the time when this is the action potential of the ventricular fibers. You see the plateau phase, the repolarization phase. So here it is at its resting membrane potential. So at the time when the action potential shows the depolarization, that is the same time when the QRS complex takes place. At that time on our action potential, when the repolarization is taking place, potassium ions moving out, that is the time when the T wave is recorded. It simply means, and I told you it is the depolarization and repolarization depends on the impulse. This this depends on this, meaning we can use this to explain this. And depolarization and entry of calcium will explain contraction. What do you say about that relationship? That during the QRS complex, the ventricles will become depolarized and they will contract. During the repolarization, this repolarization wave, the ventricles will be repolarized and they relax, meaning the contraction of the ventricles takes place at this point. That is how they found out that QRS corresponds to this, and how they found out that a T wave is a repolarization wave because it coincides with the repolarization of the action potential of the ventricular muscle fibers. Which other information can you see from this? You see these constants. Realize that the regions when the muscle is completely polarized, for example here at resting membrane potential, also the ECG is showing electric activity. You see these, they correspond, meaning if the muscles of the ventricles or muscles of the heart are having the same charge, for example here this is a polarized state, it will show you no change in voltage on the ECG. The same thing happens that during this region we are having here the ventricles are completely depolarized because depolarization took place throughout this plateau phase. They are polarized. Also, the ECG will show you a constant segment, which is the ST segment. Meaning, if the heart is completely polarized, the ECG will show you 0 millivolts. If the heart is completely repolarized, it will show you still again 0 millivolts. Yes, now that brings us to the leads. I want us to discuss why do these leads tend to show some slight differences. If you go to the precordial leaves, some are inverted, some are longer, some are shorter. What do we depend on? First, know that the standard leads, which is lead 1, lead 2, and lead 3, they are bipolar. Bipolar means they have two electrodes. For example, this is lead 1. This is its voltmeter. It has a negative electrode and positive electrode. It has both of them. That is why you're calling it bipolar. But the rest of the leads, the precordials and the augmented, they are not bipolar. They don't have both electrodes. You note that. So for lead 1, the negative the negative terminal is put on the right hand. Then the positive terminal is put on the left hand. So here on this illustration, they have put the voltages. The voltage at the left hand is 0.3 positive. The voltage at the right hand is negative 0.2. So what are you noticing? The negative terminal of lead 1 is in an area which is more negative, and the positive terminal area which is more positive. So it will give you an upward deflection. It will give you a positive potential difference. If you look at lead 2, which is this, its negative terminal is still put on the left hand. The positive terminal is put on the left leg. This is right hand, left leg. So you look at the voltage at the left leg is positive 1. Voltage at the right hand is negative. So since the negative terminal of lead 1 is in a more negative region and the positive terminal in a more positive region, it will also give you a positive deflection. You notice that? If you look at lead 3, this is lead 3. Its negative terminal, this is the negative side, is on the left hand, the positive terminal on the left leg. So since at this instant the left leg is more positive than the left hand, this is positive 1, this is 0.3, it will also give you a positive deflection. What does it mean? If this was more positive than this, it would have been to the negative side. And from these standard leads, that's how Einthoven generated the Einthoven's law. This leads you imagine that the two arms, the left hand and right hand, and the left leg, they form apices of a triangle around the heart. So this is Einthoven's triangle. This is lead 1, lead 2, lead 3. They are forming a triangle. And from area of, if you use laws of vectors, what Einthoven's law says that at a certain instant, if I know the voltages of any two of these limb leads, I can get the remaining one by summing the first two. But that is with respect to direction. For example, lead 1 is moving from right to left. Right to left. Lead 2 is moving from the right going downwards. Then this is moving from the left hand going to the left leg in this direction. Meaning when I am summing, I should pay attention to that direction. Why am I saying that? Usually summarizing that lead 2 is equal to the sum of lead 1 and lead 3. For example, this one is showing positive 1.2. And you see that this is the same as adding 0.5 and 0.7. That is Einthoven's law. So what if I have lead 2 and lead 1 and I want to find lead 3? Lead 3 is this. It moves from this point to this point. So when I'm finding lead 3, I'm going to reverse lead 1. Like I have to follow the triangle. I'm going to move from this point, I come to this apex, I come to this. Meaning lead 1 has to be reversed. Then I add on lead 2. Meaning to get lead 3, I'll get negative 0.5, the one for lead 1, and I add on lead 2, and I'll get 0.7. So it is all about paying attention to the direction. If the direction is moving opposite, the sign is reversed. So those are the standard limb leads. Einthoven's law can be seen with these illustrations. This is the ECG for lead 1, ECG for lead 2, ECG for lead 3. And I've said that from Einthoven's law, lead 2 is equal to the sum of these two. So you see, if I'm at this point, at this time, exactly through this first QRS, if I get the voltage from the baseline to this tip, and I add on the voltage here, I have to get the voltage in lead 2. You know, they're saying that at any given instant, the sum of the potentials in lead 1 and lead 3 has to give you lead 2. That means that lead 2 has the highest amplitude between the, because this is equal to the sum of these two. So it has the highest amplitudes. That's why it is preferred for interpretations, because it has more visible changes in potentials. So if you are diagnosing cardiac arrhythmias, that is abnormal heart rhythms, you can use any lead, either lead 1, lead 2, lead 3, because they are essentially the same. The P waves and T waves, they are all positive through lead 1 and lead 3. Even the QRS complexes, the major portion of the QRS is all positive, except some parts where you see lead 3 going deep to the negatives, but the basic arrangement in the same, meaning if you are diagnosing arrhythmias, you can use any. But if you are looking at damage to the ventricles, damage to the atria, pathological conditions, then the type of lead you have used matters a lot. They are, for example, when you are diagnosing, for example, anterior ventricular damage, you may find that the chest leads are more perfect at it. But for arrhythmias, any can be used. Then how do the chest leads work? The precordial leads. The precordial leads, since they are unipolar, they don't have two electrodes. It has only one electrode. And for example, if you look at this, in this illustration, for example, if I want to measure V1, I'll get the positive terminal of the voltmeter and I put it at the position of V1. That is in the fourth intercostal space at the right of the septum. Then after putting the positive at the position of V1, the negative will be a summation. Okay, you're going to combine the resistances in the right arm, left arm, and left leg. Then you combine them, you put it at the negative terminal. So in brief, it is as if we look at it at the negative terminal. Actually, it is as if it has been placed in the center of the heart. Don't know if you are seeing that. So in this illustration, measurement of the precordial leads, they measured, they didn't put the terminals at once. They first got the right arm, left leg, and left hand, and they combined them and put it the negative terminal. Then to record V1, get the positive terminal, put in position of V1. After recording it, you shift the positive terminal to the next position. You go on recording. So that's how they record their precordial leads, meaning the negative terminal is a reference point is the average of the right, left hand and left leg. That is for the precordial leads. These are the ECGs for the precordial leads: V1, V2, V3, V4, V5, V6. These are ECGs, not just KRS complex. So we looking at the ECG of just one heartbeat, meaning from one atrial contraction to the relaxation of the ventricles. These are ECGs. If you concentrate on the QRS complexes, the QRS complexes of V1 and V2, they are inverted. But from V4, V5, V6, they are upward. What would that mean from the interpretation we saw earlier? That would mean that since here we're looking at Kerr's complex, it is a depolarization, meaning that depolarizing wave in V1 and V2 is going towards the negative terminal. That is what it means. That is why they are inverted. They are going towards negative because the depolarizing wave is going towards the negative terminal. And that is seen from the position of these chest leads. You look at the position of the chest leads. These are the positions of V1. V1 and V2, they are close to the atria and they are separated by the septum. V3 is between the fourth and fifth intercostal spaces. Then we see that the septal lead is V1 and V2 because they are close to the septa. We have the anterior leads, which is V3 and V4, which are more anteriorly. Then the lateral leads, V5 and V6. V5, remember, it is at the level of the mid-clavicular line. Then V6 at the level of the axillary line. So why is it that in V1 and V2, what we are talking about, why is it that they are giving a negative deflection of ventricular depolarization? It is because when the impulse has moved from the atria going towards the ventricles, depolarization wave of the ventricles is going in this direction, not so. But I told you to imagine that since for the precordial leads, the negative terminal is as if it is in the middle of the heart. Let's say the negative terminal is at this point. When the positive terminal, for example, V1, the positive terminal is at V1 position, negative terminal in between. But you see that the depolarizing wave of ventricles is moving away from V1, not towards it. And V1 is the positive. That is why for V1 and V2, for most part of the depolarization of the ventricles, the depolarizing wave is moving away from these leads, from these precordial leads. And as we said earlier, if it is the depolarizing wave moving away from the positive terminal, that will be at negative deflection. Because depolarization wave goes with positive, repolarizing goes with negative. But if depolarizing is moving away from the positive, that is why V1 and V2 have inverted QRS complexes. Then for these V4, V5, V6, since they are more to the left of the body, and we know that the mean electric current of the heart is flowing towards the left, for them they are favored and they give a positive deflection. Lastly, on these leads, we have the augmented leads. Actually, the augmented leads themselves, they are not special leads on the electrocardiogram, that machine. We use the limb leads themselves to create these augmented leads. For example, this is AVR. To get AVR, augmented virtual lead, virtual right, we are going to use the limb lead, which is on the right itself. We leave it on the right. Then these two, we are going to combine them and put them on the negative terminal. And I told you when we combine them, we consider that the negative terminal is now in the middle of the chest, or in the middle of the heart. Meaning this is AVR. This is not bipolar, it is unipolar, because forming negative terminal, we just combined others the same way we did for the chest leads. So for AVR, it is moving in this direction, negative to positive. To get AVL, we shall leave limb lead for the left hand, we leave it there. Then we combine these two. To get AVF, the same thing. We leave the limb on the left leg. Then we get these two, we combine their wires. We combine their cords and put them on the negative terminal. That's how we come up with these augmented leads. So that's why they are sometimes called virtual leads, because they are not extra leads that are being put on the body. The total leads, they are 9, 6 precordials and 3 standard limb leads. Then this augmented, we just use the three standard limb leads. The other two are combined, one is put on the positive. That's how we form it. So for them, this is their direction. From the mid of the heart towards the left hand, from the mid of the heart towards the right hand, from the mid of the heart towards the left leg. So you see that AVF is directly perpendicular. Then something small, if you look at this illustration, it means we say that most of the time the impulse is flowing in this direction downwards. What does it mean? The depolarization wave for most of the time of the ECG is moving away from the positive terminal of AVR, because the positive terminal of AVR is this side, but the impulse is moving in this direction. That simply means AVR in normal cases must give you an inverted ECG, and that is one of the rules of the rules which were formed by Chamberlain. Because of this axis, yet you know that electric current from the heart is most of the time is flowing in this direction. So AVR will always give a negative deflection. That is why its ECG is inverted. But for AV and AVF, since the impulse is going towards the left and downwards, for them they will give you an upward deflection. So that all comes from where it determines, as I said, that you have to put in mind, as I'm interpreting this ECG, where is the negative terminal, where is the positive terminal. That is what will determine how the wave will behave. Hope that is clear. So that is the summary of the 10 rules of the normal ECG. And maybe to talk about a few. Rule number 1 is about the PRI interval. From the first illustration we had, we saw P wave is for the depolarization of the atria, and wherever depolarization takes place, that is contraction. Then the R wave is at the depolarization of the ventricles. So PRI interval is the time between the depolarization of the atria and the depolarization of the ventricles. In brief, the time between when the atria will contract and when the ventricles will contract. So this time is determined by the conduction system, the AV node, the band of His, or what we call the AV band, and the bundle branches. So just a simple view, which cases would you say that when this PRI interval is prolonged? So normally how they get the normal value, they are going to add the delay that takes place inside the AV node plus the delay that takes place in the band of His. So the AV node takes 0.09 seconds, which are equal to 90 milliseconds. Then inside the band of His, it takes 30 milliseconds, and the total gives you 120. So the least time that we expect the PRI interval to take is 120. And the greatest time normally is 200 milliseconds, or the same as 0.2 seconds. Yes, 0.2 seconds. So if you measure the PRI interval and it is beyond that limit, that means there is a problem in the conduction system. Either the AV node is compromised or the band of His. Get that. The rule number 2 talks about the width of the QRS. The width of the QRS complex gives us the time it takes for the whole ventricles to contract, because you know that the ventricles contract from the apex towards the base, and the QRS complex represents the time when the depolarization of the ventricles takes place. Meaning if the QRS is increased, that would imply a bundle branch, meaning there is a bundle branch block somewhere, or there is a problem in the Purkinje fibers, because they are the ones that have to deliver the impulse. So if the QRS is more wide, it means that either the Purkinje fibers or the bundle branches are compromised, or there is a block in this system. Yes, other rules. This rule number 5, we are talking about AVR. All waves of AVR must be negative. And the reason we have seen it that for most of the time, throughout the whole cycle, the impulse is flowing in a direction which is opposite the AVR. The depolarization waves, you'll see even the repolarization wave, it will also be flowing towards the positive terminal. And they say that if the repolarization wave flows towards the positive terminal, T wave will be down. I think that is that for those rules. Maybe something to hint about why the T wave, why is it that the T wave is upgoing. Use the illustration of the heart. Okay, let's just use this. When depolarization has taken place, when a depolarization when the depolarizing wave reaches the ventricles from the Purkinje fibers, the impulse will flow from the myocardium to the epicardium. This illustration, it will move from outwards, inwards going outwards. So when repolarization is taking place, actually the repolarization wave from it comes from outgoing in. Means the epicardium will repolarize faster than the myocardium. So the repolarizing wave will be moving in this direction. You're seeing that. So if I'm looking at lead 2, which lead 2 its negative is this side, positive it is moving in this direction. For lead 2, when the ventricles are repolarizing, the repolarizing wave is moving towards its negative terminal. It is moving towards it because its negative is on the right hand. So since the repolarizing wave is going with a negative, for which that is a positive deflection, that is why the T wave in normal cases in lead 1, lead 2, and lead 3, and in V4, V5, V6 is expected to be upward going. Why? For those leads, the repolarizing wave is going towards their negative terminals. That is why the T wave in most cases, this is the T wave, it is upward. It is a repolarization wave, but since for it is going towards the negative terminal, it is positive. So in cases where you see this T wave when it is inverted, it simply means that actually the repolarizing wave, the myocardium are the ones that have repolarized first. So the repolarizing wave is going towards the epicardium. And those are common signs of damage to the epicardium, meaning the epicardium is damaged. What else? So we usually talk about the mean axis, which we use to differentiate whether the heart is in its normal position or not. We use vectors. So this black arrow you're seeing is representing a vector, and from a vector it has magnitude and direction, meaning the longer this line, the greater the depolarization. The smaller this line, meaning a small portion has been depolarized. Whenever you see these arrows, if the arrow is small, meaning just a small portion has been depolarized. From the area introduction, we said that, that electric current flows from the depolarized region to the polarized. Where we are seeing the minus signs, it is depolarized, and from this illustration, they shaded it. Meaning for the most of the time, if you get a mean vector, to represent all vectors that are taking place inside the heart, it will be moving from the base towards the apex. And its degrees were determined to be 59 degrees from the zero baseline. This is what this illustration is showing. Then how do they measure the degrees? This circle can help you because we use it to determine the axis deviations. First of all, the degrees are measured clockwise. 0 degrees starting from this point, 90, 180, 270, 360. Meaning if they talk of a negative deviation, actually what they are meaning that the axis is now moving anti-clockwise. So if they see that the heart has been displaced negative 40 degrees, it means that from its normal position, it has moved 40 degrees anti-clockwise. If the deviation, say that deviation of positive 50 degrees, meaning from the normal position of 59 degrees, it has now moved towards the clockwise direction an extra 50, making it around 109 degrees. So whenever the vector, how they measure this, the alignment of the heart, we use this mean instantaneous vector. And the mean, normally the mean vector is in the direction of 59 degrees from the 0 degrees baseline. You're seeing that. So whenever the vector deviates, if for example, if the vector is pointing directly downwards, that will be 90 degrees. If it is moving from the left to the right, that will be 180. If it is moving upward, directly upwards, it will be 270 degrees or negative 90. So for the most of the cases, the apex of the heart, since for the most of the cases the current is moving from the base to the apex of the heart is in the positive region. In this positive, the apex of the heart remains positive for most of the depolarization wave of the ventricle. So we get this illustration and we use it to determine where each lead will be aligned, especially the augmented and limb leads. If we start from lead 1, it is the simplest. Lead 1 moves from the left. Imagine that this is left hand, right hand. Meaning it is, we use lead 1 as the 0 baseline. Then we have lead 2, which is moving from the right hand to the left leg. So from the triangle, imagine that Einthoven's triangle, we look at it as an equilateral triangle, meaning the angle between its apices is 60 degrees. So for AVR, for lead 1, since it comes from the right hand going to the left leg, we will take 60 degrees from the 0 baseline. Then for lead 3, actually this is lead 2. For lead 3, which is moving in this direction, we shall take it as 60 degrees from the 0 baseline, which is the same as 120 from this side. So this is lead 3, 120 degrees, lead 2, 60 degrees, lead 1, 0 degrees. Then we look at what of the augmented leads, how do they come up with their degrees? For the augmented leads, actually we use 30 degrees. And then you remember how we imagine that the augmented leads, they start from the middle of the heart, going towards the arms, the leg. So for AVR, you're going to get 30 degrees. 30 degrees, it is 30 degrees from the 0 baseline. You're seeing this. Then for the AVL, it will be negative 30. Why? AVL is moving upwards, going towards the left hand. I want you to imagine that this is the middle of the heart. AVR goes to the right hand, AVL goes to the left hand. So still I'm going to measure 30 degrees. For the augmented leads, use 30 degrees from the baseline. Meaning still for this AVR, this is 30 degrees from the baseline. That is how they come up with this. So this 210, actually they have, if they use AVR as 210 degrees, meaning you have measured positive from 0 moving clockwise up to this point. So you have got first 180, then you add on 30 to get the AVR as 210. If you want to use it as negative, you're going to measure this distance, which will be negative 150 degrees. But the 30 degrees I've been talking about, they are just from the baseline here. These are 30 degrees. Also for AVR, 30 degrees from the baseline. Then for AVF, for it was moving from the middle of the heart going downwards to the left leg. So for it is moving downwards, it will be at positive 90. Where you are seeing the minus signs, they are showing where the negative terminal of that lead is. Meaning for lead 3, negative terminal is this is positive terminal. And always the vector points towards the positive terminal. So that's how you can come up with these illustrations and how we can use them to determine the deviation of the heart. For some people, they may look at this illustration as maybe extra information, but actually this illustration helps you to determine the amplitude. Why do amplitudes change? You find sometimes the T wave is peaked, sometimes the T wave is low, sometimes some waves are biphasic. All those the amplitudes. If this is the vector of the electrical axis, we are going to represent it on this diagram to simplify it. So this is the vector showing how the vector is showing flow of electric impulse. So being in this direction, it is showing you that the depolarization wave is going to come and move to this side. So after drawing, for example, now we are going to use lead 1. This vector is the mean, like the average for all vectors, for everything taking place inside the heart. So how every lead from the illustration we had on the second slide, it showed that the electric impulses flows in all directions. It will flow to the left hand, left leg, to the legs. It flows in all directions. You get it? But not every lead receives the same amount of voltage. What I'm meaning is this. If I have a lead whereby our mean vector is moving almost in the same direction of that lead, it will record the highest voltage. That is why lead 2 has its waves have high amplitude. Why? Because lead 2 is in the direction of this mean vector of the heart. I don't know if you are getting that. What does it mean? Okay, let me first complete this illustration. That from this illustration, we want to determine how much voltage from this mean vector will go towards the lead 1. We want to determine how much voltage from the total voltage that has been generated by this electrical impulse is flowing towards the direction of lead 1. That is what we are using this triangle for. So this is the mean vector A. Then they draw a perpendicular line. This theory is just, you have to put it in your mind. It will make sense in the next slide. So if you have these dotted lines, they draw a perpendicular line from the baseline from this lead 1 to this vector. Then they draw a projected vector B moving in this there towards the positive terminal of the lead you are looking at. So now we are looking at lead 1, which is horizontal. So this is the projected vector B. So for us to determine the amount of voltage that will go towards lead 1, they get the distance B divided by the distance A times 2 millivolts, depending on the calibrations you are using of the ECD. Sometimes they use 1 millivolt. So they get the length of B. This is what they show: length of B divided by length of A times 2 millivolts. That is how you'll find how much current of all the total current that has been generated will go towards lead 1. That means that the longer this this A is, the longer the mean vector. If A is longer, also the current that goes this side will increase. The same happens if A is towards this. For example, if this lead A deviates towards lead 1, when they are closer to each other, when they are almost moving in the same direction, the amount of voltage recorded in lead 1 will also increase. So from that, we can use it we can use what is in lead 1 to determine the deviation of the heart. If our mean vector normally is expected at 59 degrees, if the heart, for example, deviates towards the left side and its mean vector is now close to lead 1, you will find that when you go to lead 1, it will have a higher amplitude of waves. First of all, they will be very positive since it is moving towards its positive side, and they will have high amplitudes. The reverse is true. If in this lead 1, the heart deviated towards the right and changed direction pointing this side, then the mean vector, if you draw the projected path, will be going towards the negative terminal. And when you check in lead 1, its ECG will be inverted from the normal we know. Why? Because now the mean vector of the heart is flowing in an opposite direction to the normal one. I don't know whether you are picking that concept. So that's where they get those rules that normally, since this is the mean vector, we say that lead 1, lead 2, they will give you, their normal waves. But in this case, you know that lead 1 flows in this direction. What if this mean vector started flowing in this direction? Lead 2 will be inverted. The same will be in lead 1, will be inverted. But for lead 3, it will remain positive. Actually, it will become more positive. Why? If that heart has been deviated and it is now the current is flowing in this direction from base towards apex, it is along the axis of lead 3, see this direction. So for that case, if it is a left axis deviation, which is between these degrees, between 90 and 180, lead 2 and lead 1 will be inverted, but lead 3 will not be. I don't know if you are seeing the logics they use. The differences in voltage are brought about by the differences in length. That's why I wanted to go through that. Here they have illustrated 3 leads, lead 1, lead 2, and lead 3. And they have divided depolarization into 5 stages. We have A, B, C, D, and E. So at point E, here down, the whole ventricles are depolarized, meaning now the whole ventricles have contracted. But from A, the depolarization wave was coming from the band of His. So they have drawn here, first concentrate on this illustration. This is lead 1, lead 2, lead 3. So the mean vector is this. This is the mean vector of the heart, which is now we are starting vertical polarization. So if the mean vector is flowing in this direction, you see that it is moving from the negative terminal of lead 2 towards its positive terminus. It has to be positive. If I look at lead 1, however much it is moving downwards, still it is moving from the negative terminal towards the positive terminal of lead 1. Still it will also give you a positive, an upward deflection. If you look at lead 3 is moving downwards. Actually, it is almost at 90 degrees with the mean vector. So for it will give you a little deflection, but still it will be positive since still the wave is going downwards. But I want you to concentrate on this amplitude. The amplitude in lead 2 is greater than lead 1 and lead 3. Why? The mean vector is closest to lead 2. Is almost moving in the same direction. Therefore, lead 2 receives most of the voltage more than what lead 1 and lead 3 receives. That is why its voltage is higher. We go to the second stage. The depolarization has continued. Now you're seeing where it has reached. They have drawn for you the mean vector here. Still, the mean vector is almost in the same direction with lead 2. And we see that lead 2 will be having the highest positive deflection, highest amplitude, meaning a great amount of voltage is moving in the line of lead 2 from negative to positive. But still also others will be favored. Then when half of the ventricles are depolarized, remember where I started from. That is when the wave will peak. So as depolarization continues, now the wave will start going downwards as you're seeing in position C. So you remember that from the rods we used to illustrate, when the region being studied is half polarized or half depolarized, that is when the maximum potential difference is recorded. So now as the wave is going downwards, meaning now the remaining part of the ventricles is the one that is getting depolarized. Then you go to stage D. At stage D, the left ventricle, the right ventricle, since it is smaller than left ventricle, for it has been fully depolarized. But part of the right ventricle has been fully depolarized, but part of the left ventricle is not. Meaning our main vector has now changed direction. Look at this arrow. That now most of the depolarization wave is moving towards the left. You know they are seeing that. It is moving now in this direction. So if you look at our lead 3, our main vector is moving in this direction, but lead 3 is going downwards. That is why lead 3 will give you a very negative, that for the remaining part of the QRS, lead 3 will go deeper to the negatives. Why? It is because the main vector is now almost opposite to it. So it is receiving very little voltage. So most of the voltage is going towards its negative terminal. That is why it is going to negatives. The same is for lead 2, though it is now at right angles. For it will not go deeply to the negative, it will just show at just the S wave will go slightly to the negative side, because during the latest part of the depolarization of the ventricles, the main vector of the heart, the whole electric activity of the heart, is now moving at right angles with the lead 2. So lead 2 will be receiving less voltage, but not the same as lead 3. That is the reason why when you look at lead 3, they all have the same QRS complex, the same shape, but they don't look okay. They are basically the same, but lead 3 goes more to the negatives because the latest part of depolarization of the ventricle, the main vector is moving towards the left, yet lead 3 is moving in the opposite direction. That is why it becomes more negative than the rest. Then lastly, when the heart is fully depolarized, they will all go back to zero baseline. So we started from the start of depolarization to the end. That is how you can use it to explain why different waves are different. And this is the science, this is the interpretation used to interpret the pathological ECGs. Because if you don't have this in mind, you may not be able to realize which part of the heart in the patient has been damaged. Like you can also briefly look at the T wave. Repolarization is taking place. Still, you know that repolarization starts from the apex, starts from the outwards going inwards, but the main vector will be pointing downwards. And you see that for it, the main vector is representing depolarization. So as repolarization takes place, you see it is starting from the bottom going up, from the apex going to the base. The main vector goes on reducing until it disappears. So since the repolarization waves still they do feel this illustration. This is our lead 2, lead 3, lead 1. The main vector is here. So in this position, the main vector during repolarization of the waves is closest to lead 2. Meaning when I come to lead 2, it will have the highest amplitude. If you look at difference from lead 2 and lead 1, still the main vector is closer to lead 1 than it is to lead 3. So lead 1 will have a higher amplitude than lead 3. Yes, that's the basic science. And you see it is almost perpendicular to lead 3. So lead 3 will be receiving less voltage from the total current. So these repolarization waves are positive in all of them. Why? Because the repolarizing wave is moving towards their negative terminals. The repolarization wave moves in this direction. However much the mean vector, remember I told you that this black line represents the mean vector in the whole heart. For it, at all instances, the mean vector is going downwards towards the left. It is looking at the activity in the whole heart. You get it? But when repolarization is taking place, it starts from the apex towards the base. You know that the negative terminus, for example, leading to the negative terminus on the right hand. So it is moving towards its negative terminus. That's why it is positive. And the same is for the rest. See the negative terminus. Yeah, that's basically that. Let's look at some pathological cases before we close. For example, if you have a left bundle branch, if the left bundle branch is blocked, I want you to imagine where that these bundle branches are. It means that when the impulse is coming from the AV node, most of it will first go through the right bundle branch. It means the right ventricle will contract first, will get depolarized fully before the left ventricle. These are bundle branch blocks, and that means you expect to hear, you even expect the valves of the right pump and left pump to close at different times. If the left bundle branch is blocked, meaning most impulse will first flow through the right bundle branch, meaning the left ventricle will get depolarized later, and here it is indicated 0.1 seconds after. What does that imply? You see that the contraction of the ventricles has been increased, the time of contraction. Therefore, the QRS complexes will be wide automatically. I want you to see what is happening in lead 1, lead 2, and lead 3. When the left bundle branch is blocked, then there will be a left axis deviation. That the right heart, since for it will get depolarized first, meaning the mean vector for the time when the left ventricle is uncontracting, the mean vector is pointing towards the left. The mean vector will deviate towards the left because the left bundle branch is blocked. The right ventricle will get depolarized first. Then for the remaining time of the QRS, the direction is mainly moving towards the left. That is what causes the left axis deviation. And when now this is our mean vector, it has deviated from where we are expecting it. It has now deviated more to the left. If you look at our lead 3 is negative terminal this side. That now, in this case of left bundle branch, you'll find that most voltage is moving towards the negative terminal of lead 3. That is why its QRS complexes will be inverted. You see that? For lead 2, it is almost, lead 2 is moving in this direction, but now you see it is almost perpendicular. The initial depolarization will be upward, but for the polarization of this left ventricle, which was delayed by the block, it will be downward. That is why lead 2 is showing this. You're seeing that, but for lead 1, it will not show a great effect. Why? This left axis deviation favors lead 1 because lead 1 moves from the right hand to the left hand. So for it favors lead 1. Actually, it will have highly peaked QRS complexes. You're seeing that it will have highly peaked QRS complexes. Maybe also there will be compromisation in the T waves. The T waves will also be affected. Why? Meaning even repolarization of the heart will not take place at the same time. The right ventricle will repolarize first, followed by the left ventricle. That is why also the two waves are becoming blunt. So when you know these mean vectors, you see that it is easier for you to explain how different pathological cases express. If you go to the right axis deviation for the right bundle branch block, for it will be the opposite of left bundle branch block. For it is giving you positive lead 2 and lead 3, but now it is lead 1 which is inverted. Why? When the right bundle is blocked, it means that the mean axis, electrical axis, at the time of ventricular depolarization will deviate towards the right. Why? The left ventricle will depolarize first since its bundle branch is okay. But for the left part of the QRS complex, the mean electric current will be flowing towards the left, towards the right. Sorry. The left is functioning normally, the right is taking long. So there will be a right axis deviation. A right axis deviation favors lead 3 most. While lead 3 is moving in this direction, the axis which we are expecting this side at 59 degrees has now deviated. It is now towards the right. This is the mean. Hope we are getting it. This is the mean vector. It has now deviated towards the lead 3, meaning lead 3 will give you high peaked QRS complexes, because now most of the voltage, most of the current is flowing towards its positive terminal. The same lead 2 is moving along here, meaning it has not greatly deviated from lead 2. It is still moving, it is close to it, so still it will still be giving you upward waves. But lead 1 is in this direction, negative to positive. But now the vector is moving in this quadrant. So lead 1, its waves have to be inverted. Meaning when you notice on your ECGs and look at the standard limb leads, if both of these are okay, this one is now, actually remember, this is now more peaked. More peaked is almost have the same peaks with lead 2. This is showing that now most of the current at this instant during depolarization has been flowing towards the positive terminal of lead 3. That is why it is showing a high voltage. But still, whether right bundle branch or left bundle branch, they'll all have wider QRS complexes, because generally the depolarization of the ventricles is slowed down by these bundle branch blocks. You get that? We also have pathological cases of ischemia, the apex of the ventricles, that is due to reduced oxygen supply. So actually, if you have ischemia of the ventricles, usually it is the epicardium first which is damaged. So what will happen in cases when you have ischemia of the ventricles, the bases of the ventricles, they will take a very short time to get depolarized, abnormally short period of time, meaning the QRS complex will be reduced. But during repolarization is one that will be affected. That instead of expecting the repolarization wave to move in its normal direction, it is moving in the opposite direction. Meaning now the repolarization wave will be moving towards the positive terminal. That's why the T waves get inverted. Because the epicardium is damaged, you'll find that now the repolarization wave will be moving towards the opposite side. So usually it causes T waves, or sometimes biphasic waves. Biphasic waves is when a wave is divided into two. You find that some part of the wave is upward, another one is downward. Those are the biphasic waves. But ischemia mainly causes the inversion of the T waves. Tachycardia and bradycardia, those one are easier to identify because the structure of the QRS wave of the ECG itself is not changed, but it is that the beats, now we are having fewer beats per minute, meaning you are having longer resting times, longer times when the heart is depolarized, longer times when it is repolarized, that is in bradycardia, slow heartbeat, bradycardia. So bradycardia, in cases where you have a slow heart rate, probably the synatorial node is taking long to fire impulses, or when generally the conduction system has been slowed down due to drug. You find that the impulse is flowing at a very slow rate. So you find the heart is beating slowly, or fewer beats per minute. But if someone has tachycardia, that is a rapid heartbeat, better than 100 beats per minute, the waves will be packed. Seeing these are QRS complexes, meaning wherever you see a QRS complex, that is a beat. That's a beat. So here you're having many beats per minute, here having few beats per minute. So tachycardia and bradycardia, they don't affect the shapes of the ECG. We can also talk about, it's important to talk about the blocks. If you look at, you can have the block at the synatorial node, blocks at the AV node, you can have partial blocks, you can have complete blocks. In the first year, we have shown a synatorial node block. Synatorial node block means that the impulses are not allowed to leave the synatorial node to reach the atria. What does that mean? You will have absent P waves, meaning the atria will not get depolarized. However, since the sun is not the only pacemaker, the AV node and the band of His Purkinje fibers, the rest of the conduction system is able to generate impulses. So now we'll have a slow heart rate, meaning you'll have still prolonged periods of, of where we are having no electrical activity, meaning the heart rate has been reduced. So it is only the ventricles that will be showing electrical activity. So the QRS complexes will be normal, but the P waves will be absent and the heart rate will be slow. Because these AV node band of His, they generate impulses at a slow rate. So the main sign of a synatorial node block is absence of the P waves. Then we have a first degree AV blocks, because AV blocks are in 3 degrees. For the first degree AV block, the impulse can pass through the AV node, but it is delayed abnormally. That where we expect 0.09 seconds, now we find that it is taking more time during the block. So for it will just have a prolonged PR interval. The rest of the intervals will be fine, but you'll find that this PR interval is prolonged, that the impulse takes long to reach the ventricles to get a QRS complex. So always the first degree block, if you're having greater than 0.2 seconds for this PR interval, it suggests a first degree AV block. Then if you have a second degree AV block, for which it will have dropped beats. How do you mean by dropped beats? So for the second degree, the impulse may pass through the AV node or not, meaning the block is at a higher degree than first degree. For first degree, it can pass through. For every beat, the impulse is simply delayed more, prolonging the PR interval. But for the second degree, PR will be prolonged, but for some beats, the impulse will not reach the ventricles. What does it mean? If you're having lab dab, sometimes in one beat you'll only hear lab, in another hear lab dab, meaning one beat was dropped. That's why we're meaning dropped beats. So that is second degree AV block. That in some beats, for example, in this, the impulse didn't reach the ventricles. It was totally blocked in the AV node, causing no QRS complex. So if you're not seeing a QRS complex, it means that the beat has been dropped. The impulse has simply not reached the ventricles. Because QRS complex is showing us depolarization. Depolarization cannot take place if the impulse has not reached. We get it. So sometimes the beats are dropped in rhythms. A 2-to-1 rhythm, you find that you may have 2 normal beats and 1 dropped beat. 2 normal beats and 1 dropped beat. That is 2-to-1. Sometimes 3-to-2, you find 3 normal beats, 2 dropped beats, like that in those sequences. So whenever you find dropped beats, meaning you can even get it using the stethoscope. You find that someone you are listening to their heartbeats, then you find that sometimes the beats are being dropped. It means that there is a serious block in the AV block. That is second degree AV block. Then for the third degree block, the impulses don't reach completely. They don't reach completely to the ventricles. What that means, that you'll be having the P waves, the atria they contract, but the ventricles, okay, in this case, the ventricles will not completely cease to contract because they have the AV node can also generate impulses, the band of His, the Purkinje fibers. So what the ventricles will resort to, they will now resort to the heart rate of the Purkinje fibers. They will resort to 40 beats per minute. So it will take long to see QRS complexes, but you will see P waves, then you hear a QRS complex. So in this case, it is not a dropped, you may not look at it as a dropped heartbeat, but in this case, the AV block was completely blocked. So the atria are contracting independent of the ventricle. That's the complete AV block. Maybe we can also talk about the atrial flutters and atrial fibrillation. In fibrillation, we are having the waves are moving in abnormal directions. You can find that at one instant the impulse is moving towards the left, another instance towards the right. So it causes disorganized contraction of the heart. You may find in if you are looking at lead 2, at some time the waves are inverted, another one there. So it does in atrial fibrillation. You look at the wave, it has no specific pattern. For example, if you look at ventricular fibrillation, there is no specific pattern because now the flow of the impulses is disorganized. If it's atrial fibrillation, you find that impulse is flowing in many directions, changes direction, changes direction. Which is ventricular, the same. So there is no specific pattern. But for atrial flutter, actually the impulse will be moving through the walls of the atria in a cycle. So still the impulse will not be flowing in the normal direction. It will take long to reach the AV node to spread to the ventricles because the impulse when it's generated in the sun, it will start cycling through the ventricular walls. So for these ventricular fibrillations, the ECG is bizarre. The waves are irregular, they are low voltage, meaning you will not see the peaks, you cannot see a QRS complex. And in these cases, that is when they advise to defibrillate using this machine. So actually for this fibrillator, how it works, they get a high voltage alternating current and they power it around the heart. You have the left and right of the heart. So what happens, it will cause the whole cells of the heart to get depolarized at the same simultaneously, they will all get depolarized, meaning still they will all repolarize at the same time. You know they are getting. So you have powered a great electric current, a high voltage alternating current. It will act as an impulse, causing the whole cells of the heart to get depolarized. Then after they will all get repolarized at the same time. So meaning they all reach the refractory period at the same time simultaneously. Then all action potentials will stop, meaning all action potentials that have been generated. Remember in fibrillation, the impulses are disorganized, they are flowing in many directions. That you look at the ECG, it is very irregular, has no specific shape. That is when they advise you to give this fibrillation. Because atrial fibrillation affects how the way the heart is functioning. You may find that now the heart is pumping in an uncoordinated way. You find the heart is not filling up normally. So what will happen? You will have conditions of ischemia or hypoxia just resulting from these fibrillations. So after they have defibrillated, when they the whole cell, all of the cells they go back to refractory period, then it will allow the pacemakers to now generate an organized action potential, probably from the synaptic node. That is how defibrillation works. So that is atrial fibrillation. So atrial fibrillation can happen due to atrial enlargement, and that may be due to problems with the heart valves, causing excess blood to dam inside the ventricles, causing them to enlarge. This with time it can predispose someone to atrial fibrillation in the synaptic node. in these cases can be led to now produce impulses in a disorganized manner. So actually what the excess damming of blood inside the ventricles may probably due to if you have regurgitations and you're having blood damming inside the atria, the walls dilate. Therefore, as the impulses are flowing towards the AV node, they will use a long conductive pathway and conduction will be slowed down. So during these periods, the synaptic node is firing impulses, but they are being slowed down. The conductive pathway is longer than normal. It can trigger atrial fibrillation. Then for the atrial flutters, as you saw that the wave is cycling, the wave is cycling around the atrial walls. It takes long to reach the AV nodes. So you'll have semi-coordinated contraction of the muscles of the atria. So you'll have that a QRS complex, you may find it following a P wave maybe once for every 2 to 3 beats. Because in some cases, the impulse will not reach the ventricles, so we'll have no QRS complexes. So here we're having the first beat, second beat, third beat, then you see a QRS complex. This is a sign of atrial flutters. Okay, this is different from the second degree blocks. It's different from the second degree block we are having dropped beats. But in this case, you are having beats where in some cases we don't have QRS complexes. You're having 2 beats, then a QRS complex, 3 beats, a QRS complex. It is because the impulse is greatly delayed inside the atrial walls. Thank you for watching.